Hello, I'm Kelvin Cabrera, and this is my artificial blood vessel presentation. A typical blood vessel I found in my research has a blood pressure of 16,000 pascals, and a normal blood flow rate will be 250 milliliters per minute. And then we'll be using a 5-time normal blood flow, which is 1250 for the simulations in SolidWorks. And the temperature is 309 Kelvin, vessel diameter 4 millimeters, and 0.75 thickness. And I have the source for all this data in the references. So for my SolidWorks simulations, I found that standard flow created minor relative pressure differences, but for the larger vessel, the 100 millimeter vessel, it has higher differences in pressure. And then when the flow was increased by 5 times, the differentials rose significantly, and the larger vessel also remained the most impacted. Turbulence and vessel length seem to play a large role in the high flow. In the stress analysis for the SolidWorks simulation, the higher flow rates created more wall stress, which is expected, and the stress levels varied. The stress varied by material, with PLA having the highest stress, PET next, and then the lowest is silicone rubber. Silicone rubber has the smallest under high flow, especially in the short vessels, and the long vessels showed a pronounced stress increase. So the materials with low stress responded better for high flow scenarios, which was the silicone rubber. So for our strain analysis in SolidWorks, we found that also the strain increased with flow rate, and there was a lot of variance between the materials. Since the silicone rubber had a high flexibility and elasticity compared to a stiffer PLA and PET, there is less stress change in those. The vessel size influences strain, is what we found. So the larger vessels showed a reduction under normal flow, but under high flow, strain initially rises and then stabilizes. The material flexibility is essential for maintaining function in dynamic conditions. So the analysis of the materials, we can say that silicone rubber operates well and below tensile limit, providing durability and safety. It handles dynamic expansion and contraction effectively, and the PLA and PET exceed tensile limits at high flow, creating a high risk of failure, which shows that the silicone rubber is the superior elastic material compared to the stiffer PLA and PET options. So I would recommend the silicone rubber for any synthetic blood vessels. So here are the 4 graphs or tables for the stress strain the 2 stress and strain graphs, and my drawings for the 3 different lengths of the blood vessel. And they all remain the same with each material in my references.